Cool. Thank you very much for joining. Today, I'm going to be talking about Vesta control panel, in particular about an admin takeover vulnerability, a critical vulnerability. And the subtitle, as you can see, is exploiting reduced entropy in bash random. If this doesn't make much sense right now, don't worry. I'll be explaining everything in the next couple of minutes. So, as I mentioned, I'm a founder and principal at ForBridge. I got a couple of certifications over the past 3 years. I started with the classic OWASP from offensive security, and then I got a few more also from offensive security like OSEP, OSW, a few in cloud security. And I've been speaking at quite a few conferences over the past couple of years, like Blue Hat, organized by Microsoft, besides conferences all over Europe and UK, OWASP Porto, and now OWASP London as well. So thank you very much, Sam, for the invitation. What we'll be talking exactly, I'll be talking about AppSec, because application security is our bread and butter at ForBridge. In particular, I'll be speaking about password reset tokens and how to attack them, because this is one of my favorite things that I like to target. Why? Because, well, it's unauthenticated attack surface, right? So if we want a critical vulnerability, there's a very good chance that we might, I mean, not necessarily there's a good chance, but the unauthenticated attack surface is a good target to start with. So, as you can probably notice, this reference is the old OWASP Top 10 from 2021. This slide probably needs a bit of a refresh because it was, this is a cryptographic failure vulnerability, and it was number 2 in OWASP Top 10 from 2021. But I think in the 2025 version, it's number 4 right now. Now, let's get to our target, Vesta control panel. It's web-based. In case you haven't heard about it, it's similar to cPanel, VHM, Plesk, which we already targeted, and we found the vulnerabilities in those panels as well. If you're interested in details, you can check our previous research on our blog. It's used to manage domains, websites, databases, clones, etc. Its structure is pretty lightweight. The way it's structured, basically, there's an API written in PHP, and what this PHP frontend does, it basically calls into some bash scripts, and these bash scripts do all the heavy lifting. And as a side note, they seem to have been acquired around the time we reported this critical vulnerability to them by a company called Outroll. This is how it looks like. It's pretty standard stuff. You will see the interface a bit later as well, because I will try to do a live demo. Hopefully that will work. As I said, you can manage the web server, DNS, mail, database, and all the other good stuff. So I found out that the source code is available on GitHub. So I said, excellent, let's do a white box pen test, right? Because I always prefer to do a white box pen test when I can, because it simply allows me to find more vulnerabilities, maybe more critical in nature, as you will see today. And it's way more helpful for me to look at the code. Also, I have to say that I do have previous experience as a PHP developer, so that's why I started my career. A couple of issues were reported previously. You can search on Mitre, and you'll find a couple of issues there. There are all sorts of issues which I guess are pretty standard in PHP applications, like command injection, argument injection, etc., all that kind of stuff. So I was wondering, like, can we find one more critical? As the saying goes, there's always one more. But before going to the critical vulnerability, I want to show you a bit about how the process went. So before discussing the actual vulnerability, let's discuss some interesting dodgy code patterns that I noticed initially. So the first one, there was a script called add cron. So I thought, add cron sounds interesting. Like, what if I can, maybe I can add a cron which will execute, I don't know, hourly and give me a reverse shell or something like that. Like, that would be nice. That was my initial thought. And I also noticed, like, it processes a lot of user input. So I'm like, maybe I can find some command injection or something like that. The one thing I noticed with this pattern that they keep using throughout the code is that there's no explicit authentication check at the top of the file, right? It only checks if the request is a post request, which is trivial to bypass, right? And then it does like a CSRF check. It checks the token from the post request if it's equal to the token in session. So like it's a standard CSRF check. Again, this is not a problem for an attacker. And then they do some good stuff, right? When they process all the input here, they pass it through escape shell arg, which is good. Like that's a good pattern for the developers. So good for them. Now, if we look at the bottom, it calls the function exec. It calls this script called add cron job, and then it passes all these variables. Now, one thing that you will notice here is that the user variable is not going through escape shell arg, but all the other variables are going through escape shell arg. So I thought like, maybe we can do something about injecting in user or something like that. So I was like, okay, interesting. That could be an option. So I was like, let's see, where does the user variable come from? And it comes from the session. So I thought, one interesting idea that I had was maybe I can find like a session pollution type of vulnerability, which are pretty rare to find, to be honest, but I've seen it happening. So I couldn't find anything like that, couldn't bypass this to inject anything into user. So this proved to be a dead end, but anyway, it was like interesting to research. So now let's look at the second dodgy code pattern that I noticed. Now this is in a script called gen SSL cert. So as you can imagine, this is used to generate TLS certificates from the server, right? Because when you have a panel like this, you're managing multiple domains. And one of the things that you want to do is to be able to generate TLS certificates for these websites, right? Again, there's no authentication, no explicit authentication check at the top. So basically, I was able to call this script at will, unauthenticated. So I was able to generate as many TLS certificates that I wanted, and they were stored somewhere on the file system. Another idea that I had here, again, they're using escape shell arg. So I thought, okay, maybe I can find like a 0-day in escape shell arg or something like that. So I wrote some fuzzers in PHP and also in C using libfuzzer to fuzz escape shell arg. But again, I didn't have any luck. I guess, to be fair, there were a lot of bugs in escape shell arg in the past. You can search like the PHP bugs tracker and you will see that it was heavily targeted in the past couple of years. Cool. So now let's get to the main issue, the password reset process. So when you try to reset the password, you get an email like this, which, as you can see here, contains the user, which is admin, because I'm trying to target the admin user, right? And then there's a secret code, this code. And this is exactly what I'm interested in. So the question is, how is this code generated? Let's see. First of all, I looked into the index.php file in the reset folder. So what does this do basically? When a user tries to reset his password, it submits this code that you've seen in the previous email, right? And then essentially what the script does, every user has an associated file on the file system. And this file on the file system contains an R key, which is basically the same password reset token or the same password reset code that you've seen in the email. So it checks if the value from the file is equal to the code from the email. If these two are equals, it means, okay, so the user has the right code. I'm going to let him reset his password. That's what this does, basically. So again, this is how the file looks in the file system, right? The admin user and any end user has a similar file. And at the bottom here, you see the password, which is stored in MD5. Now, this is a different issue, but we're not gonna look into that today. And at the bottom is the R key, which is the code, the password reset token that you've seen in the email. Now, an important observation that I have to make here, this code is generated once at installation time, right? So that's where the first version of the code comes from. And then every time the user successfully resets his password, a new code will be generated, will be stored in this file, and it will be used at the next password reset, okay? So essentially, you can't just go to the forgot link, try to trigger the reset password, and receive like a different code. No, you have to complete the password reset process to generate a new code, okay? So once the user submits the correct code, this bash script is called, because like I said, every PHP script calls into a bash script. So what does this bash script do? It does two things. First of all, it changes so it calculates the next password reset token here using a function called generate password, which we'll look at in a bit, yeah. And then it also updates the user with MD5 of the new password. So R key, which is the password reset token, is generated with this function called generate password. So let's analyze this function. What does this bash function called generate password do? First of all, it uses the random variable in PHP, right? And then it has this char set, which is basically alphanumeric characters from A to Z, and it randomly generates a string of length 10 characters by default, I think, right? So it uses random here, okay? Random generates a value between 0 and 32,767. Then it uses the modulo operator to choose an index somewhere between the length of this string, right? And it does this like 10 times to generate a new password reset token. So obviously, I did a bit of Google about random. I realized quickly, okay, this is not crypto secure. And I found this tool on GitHub, which is written by a gentleman called Julian Walter. The tool is called Bash Random Cracker. So essentially, this guy created this tool, which we can use to find the seed of the random number generator. And we can also use it to predict some random values. Oh, sorry. Let me have some water first. So, as you can see in the first example, if we call this tool bash and crack with 3 random values, it will discover that the seed was this one, 2 billion something, a very long number, and then it will also predict the next 3 random values, right? Basically, it says if you call random again, you'll get these 3 values. And you can see these 3 values here match with these three random values. So this is pretty cool, pretty useful. And also, the random is deterministic, and you can seed it yourself. And if you seed it with a certain value, you'll always get the same output. So you can see here, I seed it with 1, 3, 3, 7. I do echo 3 randoms, and I get these values. And then I repeat the process here, and again, I get the same values. So it's deterministic, which is very good for us. So I looked at the tool, and I wrote something similar for myself in Rust. I'm not much of a Rust coder, so it is what it is, but it works. This is basically the function that calculates the next seed. Essentially, the first value, it checks if the seed is 0, or if this wasn't initialized, it uses this static value, and then it does some very basic math operations on it. And then it returns the new seed. And here on the left, essentially is the algorithm that generates the next random number. So again, pretty standard stuff. I'm not sure how visible it is. The only check here, again, there's nothing non-deterministic here. It does a simple check somewhere. It basically checks if the random that I just generated is equal to the previous random number that I generated. And if so, it calls itself again. So basically it checks to not duplicate, not return the same number twice. So I'm like, okay, so far so good. The next question that I had was, I had to do a dive into bash internals, because the question was, okay, the generator is deterministic, but how is it actually seeded? So I downloaded the bash source code, I started looking through it, and I found this function called seedRand, which is used for seeding the random number generator. So if you look at this function, it calls get time of day, right? Okay. Which basically returns the current timestamp and the current microsecond. Again, these are all very deterministic values. So these are a bad idea to use in a security-sensitive operation. And then it calls the function sbrand, which essentially passes as parameter the current second XORed with the current microsecond, and also XORed with the current PID. Now, you notice I highlighted this. This is exactly where the main issue is, but it took me quite a long time to figure it out. So I'm not going to spoil it yet, just so you know that's where the issue is. So I started thinking of a plan. My first plan was to brute force 4.3 billion values. Like, why 4.3? It's because if you look here, the seed is an unsigned long integer. So the domain for that is like 4.3 billion values. That's why. Now, this would take like a very long time. Brute forcing 4.3 values, very long time. So bad idea, very noisy as well. Now, a couple of observations. As you noticed, getPID is called. Now, getPID in general, it's stored on 2 bytes, and it's a small value. It's easy to brute force. Now, let's talk about microseconds. Microseconds are between 0 and 1 million. So these are stored on 20 bits. 20 bits are enough, and this is also easy to brute force. So the only remaining thing to discuss is the timestamp. So the question that I had, is it possible to obtain like an information leak here? So I started to look at various endpoints, and I discovered that there were some of them that were exposing useful timestamps. What do I mean by useful timestamp? A useful timestamp is a timestamp which is exactly or around the moment in time where the last password reset was done. That would be like a useful timestamp. Anyway, all these endpoints were authenticated. So anyway, those are all my ideas. Like, if you guys have any other ideas or know any other tricks, feel free to share them. So I was completely out of ideas. And what do I do when I'm out of ideas and I'm auditing like a PHP project? I start looking into PHP internals. This is something like I regularly do. So I was looking at some PHP functions, which are also like pseudo-random, just to research. So I found this function called LCG. Now LCG returns some pseudo-random values, and as you can see here, it uses a macro called LCG, yeah, and it's got like one value here, S1, and another value, S2. The most important part here is when it sets S1 to seconds, so the timestamp, XORed with microseconds, left bit shift by 11. And then S2, similar. It does again with an XOR with microseconds, left bit shift by 11. So I'm like, that's interesting. Like, what's with this left bit shift? Like, why do they do this? And I kept thinking of this for a long time, actually. So, because it seemed like I couldn't put my finger on it, but I knew like it has to be something important from a security perspective. So I kept comparing in my head the way PHP seeding is done versus the way the bash seeding is done. So in bash, there is no bit shift. We're simply XORing free values. Is this a problem? And I highlighted again that code at the bottom, the way it's done in bash, right? It calls get time of day, and then it XORs the current second with the current microsecond and with the process ID. And after some time of thinking, I had like an eureka moment. And I realized like the issues are the following. When we put everything together, this is what we have. The current second, or the current timestamp, occupies 8 bytes. However, only 4 bytes are in practice. 4 bytes are used in practice. Like you can store any value from 1970 to 2038 on just 4 bytes. Again, the microsecond also occupies 8 bytes. However, only 20 bits are enough in practice to store 1 million values. The PID, again, occupies 4 bytes. However, I did a lot of heavy testing. The maximum value that I've seen by creating fork bombs and stuff like that was around 660,000, which needs 20 bits at most. So essentially, when we're XORing all these values, what's happening in practice, we're only changing the lower 20 bits. The upper 20 bits in the timestamp remain static. There's no bit shifting here. That's why the upper bits remain static. And that's why the PHP guys probably realized this sooner, and they implemented that left bit shift, which saved them from a lot of trouble. So this was the eureka moment. Now, I got to make an observation. Like, get PID could be the only deal breaker for an attacker, but it would have to be like an extremely high value, like in the billions, so that when you're XORing with the timestamp, it changes one of the upper bits in the timestamp. That would be like a deal breaker, but you would have to have like a computer which is running for a long time, had a lot of processes spawning and stuff like that. So in practice, like, it wasn't really an issue. So once again, the issue is summarized. We're only changing the lowest 20 bits, and this reduces the seed entropy. And in practice, the seed after XORing will fall within an interval of approximately 12 days around the current timestamp. So if I'm doing a password reset now, the XOR will create a new timestamp, which will be, today is 26, so minus 7 days ago, 19 to early March. That's about it, which is extremely limited. So now I'm going to show you how this looks like in practice, because I did like a PHP script to calculate the range where this timestamp will vary. So this is like a very simple PHP script, just some basic bitwise operations. I'm starting with the current timestamp. And here I'm masking all the lowest 20 bits. I'm setting them to 0. And then the next thing I do here at the bottom, I'm setting the lowest 20 bits to 1 to figure out the maximum value. Sorry. And this is how it looks like. So the original timestamp was like 8th of July 24. This is the minimum value where all the lowest bits are set to 0. And this is the maximum value where the lowest 20 bits are all set to 1, right? So this was, the minimum was like 29 of June, and the maximum was like 11th of July. So it varies a bit, but overall it's like 2 weeks around the original timestamp. So the first thing I did was I extended that tool from GitHub. I created like a local exploit where essentially I brute force like all 4 billion values. Now I could have optimized that, but I was just lazy, I think. And I written it in Rust, so it was extremely fast anyway. So in Rust, there wasn't really much need of an optimization because it was so fast. And the idea that I proposed here was to just brute force, let's say, for the last 3 years. Why 3 years? I think it's a reasonable assumption to say that the control panel was either set up in the last 3 years or that the admin did the password reset in the past 3 years. I think it's a reasonable assumption from my point of view. This is how the code looks like. I'm not sure how visible. Anyway, it's just like a simple brute force. It iterates over all the timestamp, 4 billion values. And basically, it checks, it finds out the seed that was used to generate a certain token. And here you can see how it looks in practice. So essentially, I tested this locally. I got this value from the local file, right? I ran my tool, and it discovered the seed that was used to generate that password reset token, or the R key value, which was like 28th of June 24. So I'm like, cool, I'm getting a result. Seems to be working. So the next thing I did, once I had this local testing done, I was like, cool, let's do it remotely. So essentially, I use Turbo Intruder, which is like a plugin for Burp Suite, which sends requests extremely fast over a custom HTTP stack. So I ported all my Rust stuff to Python. I'm brute forcing over the last 3 years. And one thing that I need to mention here, there's about 31.5 million attempts per year. So if you brute force for the last 3 years, that would make it around 95 million, or let's say 100 million, to make it a round number. So essentially, from 4.3 billion, I cut it down to 100 million, which is like a 98% optimization. So I think that's pretty good. And then if you want some other tips regarding optimizing Turbo Intruder, we can check out our other research on Concrete CMS, which was actually presented at DevSecOps last week, in case you want more speed, more optimization. And this is how it looks like with Turbo Intruder. I brute forced it over the past 3 years. And here at the top, this is the password reset token. And you can see here, what happened? Do I need a charger or something? Right, so apologies for that. I believe we were here, right? This slide. I was just saying, so I did the brute force with Turbo Intruder. You can see at the top is the token that I found. And here on the right-hand side at the bottom, you can see that I got a 200 code. And these are all the data of the administrator, right? So I'm getting a JSON with all the administrator's data. That's just what this says. So that was like a 98% optimization from where we started, simply by brute forcing the tokens, the timestamps for the last 3 years. But there's another thing that we can do here to optimize it further. So we can actually do like a social engineering trick. And you can say, let's say, you can call the victim and you can tell them something like, hey, look, I'm from Helpdesk or I'm from your hosting company, whatever, and somebody is trying to hack your account. Please reset your password. Make sure, like you said, like a really strong password that can't be brute force. Like use special characters, uppercase, lower cases, and make it like a 20 long character password. Nobody can brute force that, right? So what's going to happen? He's going to reset his password. A new ARC will be generated in that file, which the attacker can use. And when that ARC is generated, like a new password reset token, right, is generated, that will be based on the current timestamp, XORed with speed and microsecond. And as I showed earlier, it will be like within a very small interval between a week ago and a week in the future. So an attacker knows that, and he only has to brute force that 2-week interval. Okay, that's like a 1.2 million brute force attempts, which is like a 99.97 optimization from where we started. Because we started with 4.3 billion, and then if we can do this social engineering trick, we reduced it to 1 million attempts or 1.2, whatever. Now, let's see a demo. Hopefully this works. Let's see. Oh, sorry.
Can you explain what you are attacking here?
Yeah, so I'll just say. So I have Vesta set up in a container. Let me see where it is. Let me close the cup. Yeah, so this is Vesta, right? This is my target. It's set in a container on localhost port 8083. So I'm going to run this exploit, and we're going to simulate the social engineering attack that I did earlier, just to make it a bit faster, right? To make it finish in a reasonable time. Okay. No, what's going on? It's HTTPS, probably that's why. Right, so the first thing, we call the admin, right? And he set this very strong password, as you can see, right? Let's see if we can log in. We should be able to log in with it. So this is the password that admin set, yeah? Okay. Now, Where is the... Am I blind? I don't see the logout button anymore. Oh, yes. Thank you. Yeah, I am blind. Okay. So the admin reset his password, right? Now, but again, this actually made it easier for an attacker to exploit him by resetting his password. Now it's easier because he regenerated the R key, which is the password reset token. And this is based on the very, very fresh timestamp, which means a lot less brute force for the attacker to do. So let's see, brute forcing. Now you saw it started from like 150 something seconds and it keeps decreasing. And this should have worked. Let's see if this password works. So I'm admin, login with password for bridge.
Yes.
Yep, that's it. In case you're interested in other research of ours, some of our leading research insights, the concrete CMS stuff, which again I presented at DevSecOps last week, the field dating application, all your stuff was basically exposed there, but it was fixed because we worked with them, they fixed everything. And also we did some research on phishing where we extended the Evil Jinx toolkit. Questions?
Yeah.
Paul, yes.